Now, part 7, differential operator. Lecture 1, the divergence theorem of Gauss. Attention now. You see that this theorem of Gauss is invariant, which does not depend on the coordinate system. Now, what says the divergence theorem of Gauss? It states that if V is the volume bounded by the surface, a closed surface S, and V is a vector function, okay? The vector function, this means that the vector V depends on the position vector, okay? Now, a position here, position vector, with continuous derivative, then or thus, okay, integral over the volume of divergence of V. You see, this here, we say divergence of V, okay? You can write divergence V. dV is the volume element. This volume integral can be related for a closed surface, okay, to the surface over here, which is V dot n ds. ds is the scalar, okay, element of area, where n is the positive outward draw normal to S, to the surface S. Since this is invariant, okay, then we can demonstrate this theorem just using Cartesian coordinates. It will be easiest, okay, way to do it. Okay, let's then develop this using Cartesian coordinates. Okay, this is a Cartesian system, okay. E1, E2, and E3 are orthonormal vectors, okay? Okay, they're orthogonal and the magnitude is 1. Then EI dot EJ is delta IJ, okay? As we saw this in the previous lecture, okay? Now, let's consider this element over here, okay? Then you have six faces, and one volume, okay? Let's consider the first. You see the area, okay? This area over here, and on the back, the area on the back there, okay? On the x1 direction, see x1 direction. Okay, this rectangular is located at x1 plus delta x1, and the rectangular behind is located at x1. You see? Now, attention now, n is a normal, okay, outward draw. You see, it's outward, okay? This n over here is in the x1 direction, but this is the opposite, okay, because it's outward. And this is the vector, the component of the Cartesian component in the x1 direction, okay? E1 is the same, U1 is the same in the same direction, x1 direction. So this surface here is located at x plus delta x1. You see this x1. Then I have x1 plus delta x1. The surface behind, on the back, is located at x1. You see, the back is x1, and the front here is x1 plus delta x1. So what I will derive for this x1 direction, analogous you can do for x2 and x3 direction. Okay? Now, let's sum, okay, through all these six surfaces. First, you have these two surfaces, okay? Now, attention now. The area, okay, in this x1 direction is delta x2 times delta x3. The same area on the back. Okay, the same area on the back. You see, this is a component V1, x1 at x1 plus delta x1, and this is a component V1 at x2. The area is delta x2, delta x3. Okay, they are the same area. Okay, but this sign here comes from the fact that n is outward. N dot U1 is a negative because the magnitude of n is also a unit vector. Unit dot U1 dot n in this case is negative because U1 is pointing on the right. The vector n is outward. Okay? This one, the direction of n is the same of U1. That's why it's plus over here. You see, plus here and minus there. Times the area. Now, you see, I will make a permutation. Okay? Look, after 1 is 2. Then after 2 is 1. It's 3. Pardon. It's 3. After 3 is 1. Minus V2 delta x3 delta x1. You see, this is at x2 plus delta x2, and this is at x2. The same, okay? Now, plus, now, you see, this here till now is 4 surface. Okay, we need 2 more surface. Okay, let's rotate this. V2, this is V3 at x3 plus delta x3 minus times the area. Okay, the area is, you see, after x3 comes x1. After x1 comes x2 minus V3 at x3. Now delta after 3 is x1. This is x2. Now let's apply the Taylor series, okay, in the x1 direction. Okay, this is a Taylor series. The Taylor series. You have a function of x plus delta x is equal to a function of x plus partial derivative of this function with respect to x delta x. That's a Taylor series. Okay, I will apply Taylor series here. This leads to this relation here. Remember, delta x1, okay, times delta x2 is delta v, clearly. Likewise, you can use the Taylor series on this difference over here, okay? So this will be here, partial of v2 respect to x2. Now, the same volume. You see, because if you use the Taylor series here, this will leads to delta x2. We'll multiply by this is delta v. Okay? Likewise, so I can write this as, I have the same delta v. Okay? Then I have here partial of v1 respect to x1 plus partial of v2 respect to x2 plus partial v3 respect to x3 delta v. You see, this is delta v. Okay, the green one would appear when I use the Taylor series. Okay, Taylor series exactly what I do here. It's here and here. So this is the divergence of V. Okay? Now, you see, I related the surface sum, the surface integral, to the integral in the volume. So I can write, okay, let's write over here, okay? From this, okay, we say that integral of, in this case, V dot n ds, this is equal integral of divergence of V, in this case, dV. See this divergence, okay? That's it. So I demonstrate, attention now, this over here is invariant. See? I will obtain, this is S, this is V. I will obtain this using Cartesian coordinates. As soon as I will obtain this relation, I forget, okay, which coordinate system I used to come up to this. So this is Divergence Theorem of Gauss. Okay, this one. It relates the surface, the integral of the surface, to the integral of the volume. Exactly what states over here. Okay, so that is proof. Remember that n is always outward. Okay, it's just a very, very important this. Okay, ds is the area element